let me start by first of all explaining why we need to define scattering parameters. After all, many of you may already be familiar with defining essentially Z or Y parameters for a network that are primarily useful when you can define voltages and currents. The issue, however, we have when the frequency gets really high, when we have microwave networks, is that defining voltages is actually hard, and sometimes it's even impossible. For example, if you don't have a TM mode, you have to be very careful to define a voltage uniquely. So in general, we try to avoid defining voltages, or at least relying on voltages alone to describe a network. Even if you actually can define a voltage, it's really interesting that in many networks, the question is, what exactly do you define the voltage? And more importantly, what exactly do you measure it? For example, if you take, let's say, a low-frequency approach of taking an oscilloscope, and you're trying to measure, let's say, the voltage of a device by essentially connecting a cable to this oscilloscope and then connecting that to your device under test, you will very quickly realize that the result that you're getting at the instrument, meaning right here at the port, is not necessarily the same voltage that you have here. Why? Because you might have some length, which, as we know in microwave frequencies, is actually substantial. After all, even a lambda by 10 will actually give you a significant phase shift on the Smith chart. So even if you can define voltages, measuring them becomes a real trouble. So the other, thing that we have in microwave networks, the other card we can play, is power. The great thing about power is that if you can envision a power flow along a transmission line, that power flow remains primarily constant, which of course is true only on a lossless network, but also approximately true on a low loss network. So it's really this power that will help us define meaningful parameters that we can measure and calculate. And measurements are also very, very critical. So don't simply assume that measuring voltages, as I mentioned before, is easy, but measuring power is a lot easier. So let's go ahead and use our definitions here to find out exactly how we're going to define our S parameters. First, let's consider a linear network with n ports, and we will allow ourselves at this point to have each impedance of the port to be different from every other. So the impedance, for example, in port 1 is Z0 the impedance in port 2 is Z0 and the impedance in port n is Z0 n. In many networks, those impedances are the same, but in some, they're not. And later on, we will actually see examples where the impedances are not the same. We're going to essentially start by defining what is known as power waves. And power waves are usually shown with the letters A and B. And so essentially a power wave into port K, known as AK, will be the incident wave into that port. So for example, the power wave A1 is the power wave that is incident into port 1, while B1 is the power wave that gets reflected from the network into the same port. And if you look at the defining equations into this blue box here, you will find out that those are primarily based on our familiar forward and backward or reflected voltages. So if V1 plus is the forward voltage that is incident in port 1, then A1 is nothing else but this V1 plus divided by the square root of the characteristic impedance of that port. Similarly, B1 will be nothing else but the reflected voltage in port 1 divided also by the characteristic impedance. You can also define exactly the same power waves based not just on the voltages but on currents. So A1 will be I1 plus, the incident current wave, multiplied now by the characteristic impedance Z0 Similarly, B1 will be equal to I1 minus, the reflected current wave, also now multiplied with the characteristic impedance of the port Z0 Now, I also wanted to highlight here that the voltages that you see and the currents that you see here are basically RMS value. Now, at first sight, it might appear as a little bit redundant to define A1 and B1 since we already have V1 and I1. V1 plus and I1 plus and V1 minus and I1 minus. So why do we actually define those waves? Well, the reason we define those waves is that once you define those waves, calculating the incident and reflected powers, P1 plus and P1 minus, actually becomes very, very simple. We do know that P1 plus will be equal to the incident voltage square, RMS value, divided by the characteristic impedance of the port, written right here, which based on the above definition, that becomes nothing else but A1 square. Similarly, the reflected power into port 1 will be equal to BK square. So the reason we defined those waves, those power waves, A1 and B1, or AK and BK, is precisely because now our powers, which, as I mentioned before, are relatively easy to measure, are now becoming proportional to magnitude A1 square and magnitude B1 square. If you really want to know how much power is absorbed by this network from any given port, then all you have to do is now subtract B from A. So specifically, if we're looking, for example, at the power that the network is absorbing through port 1, all you have to do is take the incident power into that port, which will be equal to A1 square, and simply subtract the reflected power from that port, B1 square. Of course, the same calculation can happen in any other port. Now, if you're wondering, okay, what if I really want to define my voltages, V and I, voltage and currents for every port? Well, if you really want to find the voltages, and you can see here V1 is the voltage in port 1 and I1 is the current in port 1, then all you have to do is do what we have done before. So the V1, for example, will be V1 plus V1 minus, which now, based on the power wave definition, will be given by A1 plus B1 multiplied by the square root of the characteristic impedance of port 1. Similarly, if you ask for the total current IK, that will also end up being equal to AK plus BK divided by the characteristic impedance of Z naught. So now we basically have a really easy way to measure the power, or at least to express the power that we can measure from the lab as a function of the forward and backward waves. And forward and backward waves can be expressed as A and B based on the definitions that we see here. One clarification I would like to make about the graph that you see here is that even though I'm drawing those transmission lines to emphasize the ports from this network, the lengths of these transmission lines are assumed to be 0 in this particular case. If you do have a significant length of a transmission line, then obviously the voltage that I'm having here is not the same as the voltage that I'm having here. And in that case, you do need to shift the planes at which you define those voltages. This is something we will not cover in this class. In other words, we're not going to cover shifting of the planes in this class. But the good thing is that there is such a thing that can happen. For right now, simply assume that the physical length or electrical length are practically 0. And so that means that the network is small compared to the wavelength. Now, once you know those waves, A and B, then you can essentially relate the B and A, meaning the reflected power, which is expressed by B, and the incident power, which is expressed by A, by this new matrix that we call S matrix or scattering matrix. So in other words, the scattering matrix is nothing else but a pretty useful matrix that allows you to write the reflected power waves as a function of the incident power waves. Remember that A is also the incident wave, is always the incident wave in every port, and B is always the reflected wave from every port. So you might ask the question now, how can we get those S parameters? So those S parameters can actually be either calculated analytically, and we will spend some time doing that. So I'll show you a few different examples of how we can do this. They can also be calculated numerically by using any of the advanced numerical codes. There are commercial codes these days that you can use to solve a very complicated electromagnetic or RF network. And more importantly, they're incredibly easy to measure using commercially available techniques. I'll show you a couple of examples later on of what kind of instruments we use to measure those scattering parameters. In real life, we use a combination of those above techniques. We typically start by essentially analyzing the S parameters by doing some simple calculations. Then we rely on a numerical tool to essentially give us a more accurate estimation of the S parameters. And of course, once we design our device, we always need to measure things to make sure that what we designed is indeed performing the function that we want.